Good evening, everyone. I think we can wait for 2 more minutes so that everyone can join. We'll start, sorry for getting it delayed. We'll start within 2-3 minutes. Okay, so let's start our today's event. A very good evening to all. I am much delighted to offer a hearty welcome to all on the behalf of DSC team for joining us today. So now first let me tell you about our Developer Students Club. We are Developer Students Club, Bharatiya Vidyapeeth College of Engineering, which was established in February 2019. It is a Google developer program for university students to learn in the domain of mobile development, web development, machine learning, and cloud. We also help encourage different other domains like competitive programming, ethical learning, AR, VR, etc. Now, moving ahead, I would love to make our audience aware about our ongoing event, Ode to Code. So, what is Ode to Code? Ode to Code is a collectively effort of designers, developers to code, plan, and assemble the creative combinations that tackle certifiable issues. A great and engaging opportunity that will give tremendous insight on how to come up with innovative ideas. There are topics provided on which you can think or of how building a website, code to change the view, or other different designs. It gives a view of self-articulation and inventiveness through innovations. So, Ode to Code is your place to grow your abilities and come up with something innovative, fun, and marvelous. Now, moving ahead, I would like to introduce our today's speaker, Ashutosh Pandey. Ashutosh Pandey is a LFX Mentee at ELISA, the Linux Foundation. He has been a Google Summer of Code participant in the past. He was one of the 10 individuals in the world and the only Indian selected by Element 14 to run a BBC Micro Bit Summer Code Club. When he is not tinkering with electronics, he enjoys participating in hackathons, participating in tech communities, and dreaming of how to make a better India. So he is with us. Hello, Ashutosh. We are glad to
Uh,
have you here with us.
yeah, hi, I'm glad to be here. Hello, everyone. And should we start?
Yeah, we should start our presentation.
Yeah. So, guys, I'll be sharing my screen with you. Since we have a limited time frame, I've prepared some slides. And you know what? Think of this session as an intro to what you can Google or what you can search for. That's all that it is. It's a very high level overview of hacking on hardware. So that being said, let's stop streaming my face and start the screen. If
Yeah,
I'm
so
currently,
basically,
yeah,
your topic is the IoT and edge computing, right?
yes.
Okay,
So we'll be
fine.
talking about hardware and IoT and edge computing. So I'm currently in a village in East UP. So if you hear random cow noises or tractor noises, please don't freak out. It's how it is. So that being said, let's start. I'll allow it.
Yeah, it's
Can
visible. You
the
can start the presentation.
yeah, I can start, right? Okay, wait, what
Yeah.
happened? Yeah, right here. Yeah. So welcome to hardware hacking, guys, and it's about IoT and edge computing. So today we're going to work on talk about a very unique subject. I know that hackathons are very software focused, and computer science guys love to code, but here we're going to look at something different. We are going to learn a look on how to work on hardware. Say you have to build a hardware project. How do you go about doing something like that? So an introduction to me, just a little bit about myself. I'm a final year CSE undergrad at DSE Bangalore. It's a college in Bangalore. This summer, I did Google Summer of Code with Arduino. I was one of the two students who worked with Arduino over the summer. My project was to develop a transcompiler to convert a subset of C++ to Python. Basically, Arduino released a few new boards, and those boards run Python. But all of Arduino's current libraries are written in C++. So I wrote a tool to automate some part of that process. Currently, I'm working with the Linux Foundation as a mentee for ELISA, which stands for Enabling Linux in Safety Applications. And this is with Intel Mobileye. So basically, here what I'm doing is I'm again working on the GCC compiler and glibc to scan a part of the GCC compiler and the GNU C library for bugs and all that. In my last summer, I worked as a summer code club intern with Element 14. Element 14 is the company that makes stuff like Raspberry Pi and some Arduinos, so they're hardware manufacturers. I ran a code club in India where I taught 6th to 8th grade kids how to code using microcontrollers, and I also participated and won the Smart India Hackathon Hardware Edition in 2019, and there's some other stuff. So that's about me. So here's an introduction to what we are going to talk about, and you know why it's like the hardware development process can be a lot more intimidating than the software process. Like if any of you have tried building an say an Arduino based project or a project with a few sensors, it can be intimidating. First of all, because you're dealing with hardware and you have to worry about two kinds of issues: hardware issues and software issues. If you're if you're ever programming and you run into a bug, The only thing you need to do is just, like run the program again, change something, keep modifying it until you get it working right. With hardware, if you break your hardware, you just lose money. And there's a lot of choices, like depending on what you want to do, you can use an Arduino, a Raspberry Pi, an STM32 board, a BeagleBone, uh, or and again, in within these board there are several sub boards. And there again, if you want to measure temperature, there are multiple different sensors for it. If you want to measure humidity, there's multiple different ways to go about it. There's multiple different communication protocols. In fact, there's multiple different languages. At least if you are going to do machine learning, a reasonable first step would be to learn Python, for example. But with hardware, you can't be sure. Depending on which board you're working with, you might have to learn embedded C, Arduino, or even Python or some other combination of other languages. So basically, IoT or hardware is it's not a standardized field. There's no universal standard for what languages you can use, or some universal standard where all libraries are written. Everything varies according to your application. And obviously there's monetary issues. Stuff can be expensive, and it can be hard to find, depending on where you live. So that's there. And then there's a whole lot of debugging. Hardware debugging is just double the work, right? You have to check for software bugs and you have to check for hardware bugs. You can never be too sure where the bug originates from. So this also makes it tedious because stuff stops working. And unlike a PC where you at least get an error message, if your microcontroller isn't blinking or is just flashing a red light, it can mean 100 different things. So that's also there. So given that all these problems exist, why even work on hardware? Like, what's in it for you? So one thing is you get a chance to really understand how a computer works. Yeah, like really understand how it works is when you write a program and to the stage it's printed on the screen. What actually goes on? What actually reaches the processor? What kind of instructions does it execute? You get to understand stuff at a very very low level, and this lets you see programming in a whole new light. Why programming languages are designed the way they are, why stuff is the way it is, why we use binary and all such things. And the second thing is it allows you to bring your ideas from paper to reality. On the left side on the screen right now, you can see a our project for Smart India Hackathon. That's the grand finale stage. This is from last year, 2019. So, it happened in person. We'd watched, me and my friends, we had watched Avengers Infinity War, just like everyone else. And we thought, like, let's build an Infinity Gauntlet type of thing that can track unconventional exercises like push ups, sit ups, barbell curls, and all that. So, because I had a friend who knew designing, 3D designing, all of those parts you see on the left, they're custom 3D printed. On the right, there's another project from another competition I took part in where me and my friend designed a whole prosthetic arm that works with only one servo motor and can replicate an entire arm's worth of movement. So we were able to think of an idea, come on, like let's make this kind of thing and actually execute it. We could actually, think of something and make it happen. So that's what makes it so cool in my opinion. You learn how to work on hardware, you learn a bit of designing, and suddenly anything that is possible to make, you can build it. That's because now you have very powerful components available that can simplify a lot of the work. With single board computers like the Raspberry Pi, you have a whole lot of compute power in your pocket. So anything that you can think of, you can build, and I think that alone makes the grind worth it. So now one thing that people ignore is that the reason is the one of the reasons, for example, that we all don't like our college syllabus so much is because it's backwards. They teach stuff that you were supposed to know like 20 years ago, and you're learning it now, so it doesn't seem very useful to you. The thing with IoT is, for some reason, college level and intro level IoT courses are still stuck using the board on the left. Even if you see most tutorials, they're stuck using the board on the left, which is the Arduino Uno. But hardware has changed. Even microcontroller level, low level hardware has changed a lot over the years. I don't think I need to tell you how PC hardware has changed in the last 10 years, but microcontrollers have changed a lot too. Now let's compare the board on the left to the board on the right. So compared to the Arduino Uno, which is the big board we saw, to the Nano BLE 33 cents, these two boards launched 10 years apart. Now both of these boards consume roughly the same amount of power, but the second board is 4 times faster, has 250 times more memory, has 128 times more static RAM. It weighs just one fifth of the first board, and the board even comes with seven sensors integrated. So you don't even need to buy a whole box of sensors. You have a microphone, a proximity sensor that tells how close it is to objects, an IMU, which is basically a fancy word for a GPS or for a gyroscope, and an accelerometer, a light sensor, a barometer, which can also calculate your altitude, a temperature sensor, and a humidity sensor. And because this board has so much memory, it has support for real-time OSs. Now, what real-time operating systems are, we'll come to that later. And this is just one example. There are even more overpowered microcontrollers like the Arduino Portenta, which can even run Debian. Like a microcontroller can run a whole operating system like Debian. And then Raspberry Pi, there's a $5 Raspberry Pi Zero that's thousands of times faster than this also. And now microcontrollers can even run machine learning models with TinyML. You can even run neural networks, and you can do computing on the edge. So that's how far we've come. So now we basically start with the question, like with the premise of this talk, that is there a method to this madness? Because IoT involves so many different things. It involves stuff like obviously embedded systems, which is your electronic stuff. It involves machine learning if you need that. It involves dealing with communications networks. If you're designing networks, you need to know some cloud stuff. If you're dealing with the cloud, you need to know about processor scheduling and some OS concepts. So, depending on how much data is involved, you might even go into the big data territory, especially if you're deploying something on a wide scale. So, because of the sheer number of domains involved, it can be very hard to figure out how to actually go about building a hardware project. But luckily, there's an algorithmic way, or there's a method in which you can think and reason out how to work, or how to get stuff done. So so basically, first, where do you start? You define a problem, as in, this is what I'm going to build. You need to think about what you're going to build, and you need to think very hard. And this is the hardest step, because compared to software development, where you can always add features on the fly, or you can add features in the middle, in hardware development, features are money. And features have, sometimes what you're building can have space constraints, time constraints, power constraints. So, unlike a software project where you can basically start with an outline and then go deeper into that, and expand upon that idea, or even change the course of your plan, in hardware, it's very necessary to have a very, very clear plan of what you're developing before you actually start building or buying anything. Because depending on this will change entirely the cost, the way you build the hardware, what you do with the hardware, what your hardware can do, how many changes it can accommodate. So you need to define a problem. Say you think that you have to say build an exercise tracker. So the first step is you have to think in terms of variables. What kind of variables? I'm not referring to data type variables. I'm talking about stuff like what can you measure with the sensor. So you need to think, say you are wearing a smartwatch on your hand. Realistically, from one point in your wrist, what can you measure? You can measure your acceleration along the XYZ axis. You can measure your orientation, that is your gyroscopic data. You can measure your temperature. With a little bit of work, you can measure your altitude because the air pressure around you will change the higher or lower you go. You can probably measure your pulse easily. With some extra work, you can take an ECG. So you need to think about what variables you need. Say you're building a farm management system or something that gets employed in a farm. What can you measure? You can measure the hours, like the number of hours there's sunlight out there. There's sensors that can measure relative sunlight. You can measure the humidity in the soil. Or if you're building a system for, say, a water tank, you can measure the level of water, or you can measure the pH properties of the water. So in terms of variables, you need to think, what variables are you going to measure. And more variables is not always better. Obviously, simpler solutions are cheaper and they're easier to debug. So ideally, you should think in the least number of components that can solve your problem. Like even in during Smart India Hackathon, our original prototypes, which, let me go back, all of the three that you can see on the top, all of them had a screen. The final prototype is on the bottom part of the screen, that you can see that flat white box there, and that doesn't have a screen. Why? Because when we were working, judges told us, like, your prototype is too heavy, I can't wear this and exercise. And then they asked us, like, do you really need a screen? Everyone carries a phone in their pocket, right? So what are you going to do carrying a screen? So we eliminated the screen, and with that, a large part of our UI also went. Like, obviously, we had to build an app and connect it to the cloud so that people could see the stuff on an app. But in this case, removing a feature added to something else. That was removing a lot of the weight, reducing a lot of the size, and increasing the portability. So more is not always better here. Now, analyzing existing solutions. You need to study the market. I think this works for any hackathon project, really. It's not really specific to hardware as such. If you're building something for a hackathon, then please do an analysis of what already exists. You might end up reinventing the wheel, but that won't win you anything. You need to think about what already exists and what have you built. Is it any better? For example, if we didn't specifically focus on unconventional exercises in our project, it would just end up as any fitness tracker. And a couple of, sometime later, I think now even support for unconventional exercises is there, but I think a year and a half ago it wasn't that common. So you need to really study about what exists, or in terms of, even in terms of the prosthetic hand that we built. The main factor we were trying to convince was not the fact that prosthetics already exist for the arm. They already do. The thing is, prosthetics for the arm, they cost a shit ton of money. They cost a lot of money because they have so many motors, so many electronics, and they're also heavy. So the main optimization that was going on there was cost and weight. So we tried whatever normal prosthetics could do, we tried to do it with lesser components and build it more cheaply. Again, here the case wasn't that we were building something that didn't exist, we were bettering on something that existed. So, as a general principle, there's three things that you can consider. Either what you're building should be compatible with the existing solution, or it should be compatible with the existing solution.
I think there's some network issue with our speaker. So sorry for me letting you wait. You have to wait for some time. We are really sorry. There's some network issue with our speaker. I think so. He was going very well with his topic, edge computing and in Internet of Things. So I would like to just give you an overview of edge computing. Edge computing is a distributive computing paradigm in which processing and computation are performed mainly on classified devices, nodes known as smart devices or edge devices, as opposed to processed in centralized cloud environment or data centers. It helps to provide server resources, data analysis, and artificial intelligence to data collection sources and cyber physical sources like smart sensors and actuators. And do I think some of you might be having idea of Internet of Things. Okay, I think our speaker is back, so I would enable him. He'll continue. Hello, Ashutosh.
Hello, I'm so sorry. I'm so sorry. When did I get disconnected? At which slide? Can you please
You,
let me know?
yeah, you were discussing about the problems. Uh,
Yeah, sure.
can you view the
So,
slide?
right
I'll
here,
share it.
right? Huh? Right
You
here,
view
right?
your slide. I'll share it.
Hello.
You are stuck, I
Yeah,
think
so
so.
can you hear me now?
Yeah, yeah,
Can you hear me now? Yeah, so
yeah,
can you just give me feedback every 1 minute? Can you say okay or something so that I know I didn't get
yeah,
disconnected
fine.
again?
Yeah,
Yeah,
fine, fine.
sure. So, on this slide, can you tell me where I was?
You can share your
MVP
screen.
or
It's not
something?
getting shared. Your
Uh,
screen.
yeah, yeah, sure, sure, sure. 1 minute.
Okay.
Can you see?
Yeah, yeah.
Yeah,
Defining
so
a
you can
problem.
see here, right? Yeah, yeah. So where did I stop there?
You
So,
were discussing about these
uh,
problems, right? Things, software versus hardware.
yeah, yeah. Yeah, sure. So after you like decide whether you want to build a software problem or a hardware problem, you have to make the MVP. This is basically a simple solution that you can use to prove that your prototype works. At this stage, it's not very important whether your prototype is the right weight or it looks good, or you don't have to build it with the materials you end up with. You don't have to fabricate PCBs. Breadboards work just fine. But you have to decide on you have to show that it works. That's very important. Then iterate. Now iterating just means that you have to try to do the same stuff again and
I think he got disconnected again. We are really sorry for interruption. Yeah, he's back.
try to see make sure that
Ashutosh, you
let
got,
me stop my
yeah,
yeah,
you
yeah,
stopped
I
your
know.
video.
Yeah, I figured out how to find out now. If the webcam turns off, I'm disconnected. So I just remember that. Sharing the screen and we're back.
Okay.
Okay, fine. So yeah, so after you build the MVP, you iterate. And after that, after you repeat times, you have
Your
to
slide,
release it or deploy a solution.
Ashutosh.
But
Sorry for interruption, but
is it not?
we couldn't view your slide.
Yeah.
Ashutosh, you are not audible.
Am I there? Hello.
Yeah. Are you visible and audible?
I'll try to share my screen again. Hello.
Yeah, you can continue. Till then, I would request our audience to put their questions or doubts in the comment box so we can take them later. You can turn off your camera so that your screen and be visible.
Hello.
Yeah, you
Yeah,
got
am I
started.
audible?
Yeah, yeah.
Yeah, is it working now? I'll
Uh,
try screen sharing. Otherwise, we'll have to try something else. We'll just see.
you could turn off your camera and then share the screen. So
Yeah, I turned off my camera and I've
okay, fine.
started screen sharing. Let me know when it comes on.
Yeah, we
All
can
right.
view your
Wait, is it
screen.
visible now?
Yeah.
Yeah, sure. So okay, fine. Let's just so let's continue where we left off. You have to choose the right board or platform for what you're trying to build. Now, more is not always better in this case. Sometimes, like you see the Raspberry Pi, that's a severely overpowered board. You have stuff like a 4-core processor, 8 gigabytes of RAM, two USB ports, two USB 3 ports, two USB 2 ports, a stereo jack, dual HDMI. So and sometimes these boards don't even cost that different. Like an original Arduino costs like $25, while a Raspberry Pi costs $35. So logically, people might think, why buy a board which has very less features for so much money? But the thing is, you can't always go by the spec sheet, because sometimes there are some factors that are hidden from you that are very very important. So let's take a look at some of those stuff. So what do you need to keep in mind? You need to keep in mind your power requirements and constraints. That is, how much power are you willing to work with. Something like a Raspberry Pi needs a 15-watt charger just to work. So supplying 15 watts of power, say you're building a solution that needs to be mounted somewhere outside or in some remote area where you have to power stuff with batteries, it's not very practical to do that. Second is your project time sensitive? Now, by time sensitivity, here I mean, does your project have very strict requirements for time? Say you have a car like a system, or a car autopilot, for example. That's a very good example. Tesla's autopilot. So Tesla's autopilot has to perform within time. If it doesn't return a signal, for example, sometimes you use your computer and your computer crashes, and sometimes it gets stuck. So you can live with that. But the thing is, if in an autopilot the autopilot ever stops or fails to give a signal on a time, it can cause a person to die. So that's like a real time sensitivity. Or in systems like rockets, where you need the different stages of the rocket to go apart at a very very specific time. So in such case, that's time sensitivity. So microcontrollers, stuff like Arduino's STM32 boards, they are better at time sensitive projects because they have internal clocks. Like it has suppose or an a Raspberry Pi doesn't have an RTC battery. It won't tell you the system time. Every time you switch it on, it's going to use the internet to get the time for you. And obviously, if you have to time stuff down to milliseconds and nanoseconds, you need a processor that can operate within those time constraints. So real-time operating systems are built in such a way that they will return a result within the given time frame. Maybe it will return a yes, or it will return a no, but it is going to work within the time frame. So depending on whether you need that time sensitivity or not, you can just go for one or the other. Now, what kind of sensors are you including in your project? There's two kinds of sensors: analog sensors and digital sensors. in Arduino, so something you might have seen the same pins labeled A0, A1, A2, A3, those are analog pins. The other kind of pins are the digital pins. So analog pins, they measure stuff as a function of voltage or current. Where your values can vary greatly from top to down. I mean, in a continuous motion, like hello, I am here. Okay.
Yeah.
Let's just continue and keep ignoring that every time it happens. So yeah, that's the what kind of sensors are you including? That's what depends whether you have a digital sensor or you have an analog sensor. Because some boards like Raspberry Pi do not support analog sensors. You need
Ashutosh,
to add,
you're
yeah,
sorry to interrupt. You are sharing a screen.
yeah. Is it
No,
not
it's
visible
not
yet?
edited. Yeah, no.
Uh, okay, let me see it. Sorry, I'll share my screen and I'll just, okay, allow.
Yeah,
Yeah, is it done? Okay, fine,
yeah.
cool. Yeah, so that's there. So is it time sensitive or not? Then again, what kind of sensors? Then physical constraints. Do you have a limit on how much space or weight your stuff should have? Say, especially this is very important for wearable tech or for say mobile phones or some portable gadget. How much your stuff weighs, how much space you have. This limits the kind of power supply you can use because batteries are really heavy. Then you have a data storage requirement. Uh, like do you need to store data, do you have to store it on an SD card or do you store it on a cloud? That makes a very big difference. Then weatherproofing, are your sensors up to spec? So say you're building you think that okay, I have to build a system in a tank, where I'll measure the level of water in a tank. So you choose to use an ultrasonic sensor, and sometime later you realize your ultrasonic sensor stopped working. Why? Because the inside of a tank is a very humid environment, and the sensor is not built for that kind of humidity. Similarly, very cheap moisture sensors, they use a nickel coating on the surface, and and how it measures moisture is when water comes between those electrodes, it measures the difference in electricity or the flow of current in that, and it tells you whether there's water or not. But the problem is over time that corrodes, it rusts away and it doesn't work anymore. So you need to think about that. Programming languages, again, depending on which board you use and which IDE you use, you might have to deal with different programming languages based on what you're more comfortable with. C embedded C or Arduino, which is based on top of C, are the traditional choices. Now you have stuff like MicroPython, CircuitPython, and all coming in that allow you to more easily program these boards and connecting to the cloud. That's also there. So here's a picture of some sensors. You have accelerometers, you have a gyro, you have your resistive sensor, which is basically a long coated strip of carbon where your movement can change the resistance. Your pressure switches. So there are many types of sensors. There are probably hundreds and thousands of sensors out there, but an easy way to look for them is to look for what you're trying to measure. Later on, you'll learn the name that BMP 180 is a temperature and pressure sensor. But if you search for pressure sensor, you'll get a list of different pressure sensors, and then you can start from there. So try to remember it by what you're trying to measure. The sensors out there for measuring everything from blood alcohol content to taking an ECG. So depending on what you want, you'll have to pick that. Then one more thing you need to worry about is how does your board talk to your sensors? Basically, you connect your board with wires to your sensors, right? But that process differs based on which sensor you have and how you want to communicate. Like here on the pinwheel, you can see multiple communication protocols like I2C, RS232, USB. So now how these differ is I2C is a two-wire bus. Basically, it allows you to communicate with any sensor using just two wires. But the limit is that it can be slow. It's because multiple sensors can be connected on the same pin. Each sensor needs to wait, and it needs to take its time to communicate, because there's an order. The microcontroller will read from the first sensor, then it's going to read from the second sensor, then from the third sensor, then back to the first one. So even though this occurs several hundred times per second, that might not be fast enough for you if you require very very precise measurements. One example of this is, say, a LCD screen. In LCD screens, to display any picture or video or text, you need to change the status of hundreds of pixels in a very short amount of time. So if you run an I2C, an LCD of an I2C protocol or of I2C pins, which are labeled A5 and A4 on Arduino, you are going to have a screen that refreshes very, very slowly. And I'm talking about like 1 or 2 frames per second, or 1 or 2 frames every few seconds. So then you use SPI, which is your serial peripheral interface. So the advantage of SPI is, of course, that it's much faster, but the disadvantage is one, that it needs more wires, and the second, that you can't use two three things in SPI all at once. You have CAN, which is used in cars. Your car has a bunch, like 50-60 microcontrollers inside, that coordinate everything from your braking system to your AC system. Anything that is automated by the push of a button probably has a microcontroller at the back end. Then you have USB. I think everyone knows what USB is. So depending on which board you have, how you change these and what kind of sensors you use, you need to determine what kind of protocol you'll use for which sensor. Say you have a board, a project with an LCD screen and a gas sensor or a pressure sensor. You can connect the pressure sensor and gas sensor to I2C and connect the LCD through SPI, right? So that's how you need to think. I'm still audible, right? Can you hear me? Hello?
Yeah, yeah, you're
Yeah, sure.
audible.
Yeah, sure. So now we come to wireless protocols. Now, see, since this is IoT, we're going to move into the cloud side of things from here. Now, how do you get your signal across the air? Now, there are multiple ways of doing this. The most common one is obviously Wi-Fi. Wi-Fi is everywhere, but there might be times when you don't want to use Wi-Fi. One is that most of the sensors that use Wi-Fi run Wi-Fi on the 2.4 gigahertz band, and this is a very very crowded band. Like a whole lot of devices run on 2.4 gigahertz Wi-Fi, and your sensor might pick up corruption from everything from your microwave oven to your home router. So that's there. But also, say if you have like you have a big factory and you have like 40-50 sensors split across the factory, you might not want to connect all those 40-50 sensors to Wi-Fi. You might want that, okay, let me send all those 40-50 signals to one place and then send data from there to Wi-Fi for obvious reasons. So there are other protocols. BLE is Bluetooth, and now with BLE 5, you have very low power consumption in Bluetooth. So this is why so many smartphones use Bluetooth. It was actually invented by an actress. So the fact that few people know, Hedy Lamar created Bluetooth. Then you have Zigbee and Zigbee. So Zigbee is basically a free transmitting spectrum. It's like one area of the electromagnetic spectrum. Like you might have heard of the 2G scam, where people auctioned off parts of the spectrum. So in Zigbee, you can send stuff for free to the cloud, and it has an incredibly long range. People have made Zigbee work at to up to a range of even 700 kilometers. I believe 760 kilometers or so is the record. So you can send a signal from somewhere in, say, Pune to Mumbai with a Zigbee module. But the limitation is obviously that because the distance is so long and the wavelengths involved are large, you have to stick to a very low rate of communication. And because you're not actually paying for the connection through that Zigbee mesh network or through that Zigbee protocol network, you're limited to how much data you can upload. It's limited to a few kilobytes per second or a few hundred messages per hour. So that's the limitation. Then you have 6 low WPAN, which is a modification of this. And again, on the right side, you can see what kind of a topology or in what kind of a system you can make it work. So these are the different wireless protocols, and these are supported by either by the board natively or through the module. Like some sensors come with inbuilt Wi-Fi. Like say, I mean, some boards come with inbuilt Wi-Fi, like your ESP32, while other boards you have to add them externally. So if you have a choice between using something that's integrated into the board versus adding an external dongle or module, always go for the integrated solution. It will be less of a hassle to set up stuff. Some boards even come with integrated Zigbee antennas, but usually Zigbee is added externally with an external antenna and all that. So, cloud fog in the rain. Now, cloud computing, and on one side, you have your embedded systems which don't communicate with anything. I'm still audible, right? So,
Yes, you are audible.
yeah, sure. So on one side you have cloud systems which are which can communicate with just about which communicate over directly the internet, and on the other side you have totally embedded systems which are not connected to any network whatsoever. They're completely localized, like the examples I gave before. So cloud computing basically lives inside data centers. It takes advantage of massive parallelization. Now, and edge computing is when all the computing is done on the nodes. Say you have a bunch of sensors, they read the values, they send them to the board. The board does all of the computation then and there, and then it sends the pre-processed data to the cloud. In the middle, you have fog nodes. Fog computing, as the name suggests, it's a hybrid between cloud and edge computing. If you have a fog node, so basically think of it like say your Apple smartwatch. Your Apple smartwatch needs the net to connect to work properly. It needs an iPhone that's tethered to the internet so that it can back up your data somewhere. In that sense, it's a cloud device. But the watch can also do several things on its own, like tracking your movement, tracking your exercises, tracking your sleep cycle, your ECG. So that's when it's running computations within itself. That's like edge. So this state where you pre-process some of the data and send it to the cloud while also doing some of the stuff, like sending some data to process in the cloud while also doing some level of processing on the edge. That's what fog computing stands for. Now, suppose you want to get connected to the internet, you want to build something and you want to make an app that can display value from those sensors. Suppose all you care about is basically displaying the values. You're not too worried about modifying anything, changing anything. So for stuff like this, you have IoT platforms. Basically, you have stuff like My Devices Kaine, which you can see on the left side. You have the Arduino IoT Cloud, which you can see on the right side. So what these services tell you is they just make you, say you take an Arduino board or an ESP board, you which has inbuilt Wi-Fi. You just generate a token, you paste that token in your source code, and from there you connect all the sensors. The software that they've built will automatically detect which sensors you have hooked up to your board, and then you can run it off their native app. So this is the easiest way to get started. You can make everything from temperature sensors to, like, you can sense everything from temperature to humidity to pressure to movement this way. It'll even auto generate graphs and log the data for you. However, it's not very flexible. Say you want to do computations on the data, or you want to clean the data before displaying it somewhere. This is not the ideal way to go. So if you want a little more flexibility, you can go for something like Azure. So in AWS or Azure, you have IoT devices on one end, and you have AWS services on the other end. Like, not like that. You have AWS services. So what happens in this is, for example, you have a Raspberry Pi. So what you will do is you will take AWS IoT core, which is a piece of software. You'll run it inside the Pi, and that is going to take care of the communication between your IoT devices and your AWS services. This is not going to generate a UI for you. It's just going to provide you a means to access the database of information that the sensor outputs. From there, whether you want to run machine learning on it, or whether you want to store that data, or whether you want to run, say, Unreal Extreme to do some denoising or something, that's completely up to you. You choose what you do. AWS already has its own tech stack for managing stuff. So what these do is, this does is AWS IoT provides a bridge between those devices and the service. So this is a lot more flexible. Again, if you want to go totally flexible, like you want to build everything from scratch, you can use something called MQTT. Now, MQTT stands for Message Queue Telemetry Transport. So this is based on a publish subscriber model. Think of it like as a newspaper. One person publishes the newspaper, and the other person reads it. Yeah, I'm here. Yeah, sorry.
Yeah. Actually,
Yeah,
I would request that can
yeah,
we wrap up in about 5 to 10 minutes because we also
yeah,
have our
sure,
next.
sure. Yeah,
Yeah.
sure. We're wrapping up. So this is basically a means for you to communicate with your devices through your MQTT protocol. You can build a system which sends signals from one side, and how many ever people want, they can receive it. Then you have IFTTT. So here you can set constructions like, if this happens, if this sensor reads this, then send data to Google Drive, or you can send it to some place. So you can trigger an action through this. So this is very powerful. It stands for if this, then that. It's a free web service. You can check it out. You can set up triggers based on what data you receive to do certain stuff. Then you have stuff like real-time operating systems. These allow you to run multiple programs together. They also allow you to do threading, concurrency. They allow you access to APIs and other such stuff. So you can look at free RTOS and other such services. Then you have machine learning, which on microcontrollers. So TensorFlow Lite does work well. On the right, you can see an example of a system that can detect yes or no. So the board has an inbuilt microphone, and you can hear yes or no, and I mean it'll hear yes or no and identify with some degree of certainty whether you said that or not. So this is still a rapidly advancing field in terms of what kind of neural networks we can run on this. Then here's an example to wrap things up. This is the last slide. So a guy built a system to differentiate between two audio tunes. He used something called a field programmable gate array, or an FPGA. He loaded up 100 cells with random zeros and ones. He let the algorithm reject the worst combination, and in the end, only 37 logic gates, he was able to differentiate two sounds. And it turned out that, this circuit had closed loops which were not related to any other part of the circuit, and and the circuit also depended on the PCB they were using. So this kind of approach is used to create special antennas that you can see below. Those antennas are created using this genetic algorithm method. You let the algorithm decide what form your hardware should take. So with this, we come to an end to the talk. I am so sorry for the connection issues. And if you want to connect with me, you can see the GitHub and LinkedIn on the screen. And if anyone has any questions, just leave them in the chat, or you can contact me later. Thanks.
Thank you so much, Ashutosh, for such an informational presentation. Now, moving forward, I would request our audience to ask their queries. We already have some questions, so I would be displaying it on the screen.
Yeah,
Okay, so our
so
first question is
where
from
should I look
Anish.
for good projects? Yeah,
Yeah,
so
where
this
should I
is
look for
a
a
very
good
good
project?
question. Yeah, so there are several forums on the net. One good place is Arduino's own project hub, Arduino Project Hub. Then you have the Element 14 forum. You have Hackster.io, and Circuit Digest. So these are some websites: Circuit Digest, Hackster.io, and Element 14, and Arduino's Project Hub, where you can look. These sites specifically catalog hardware projects that other people did, and after you read that, you can get started from there. So that's the answer.
Okay, so our
Yeah.
next question is from Rajkumari Devi. What languages frameworks are best suited for approaching IoT related projects?
Uh, yeah, so IoT now it works on MicroPython also, but it's a relatively new language. Your best bet is still C and C++, or and embedded C. So you need to know low-level languages very well, because that's what the most boards have support for. The other boards have, the other stuff is relatively new and it's just starting to get support. So your best bet is to stick with C and Arduino, which is a variant of C++ and C. That's it.
Okay, so our next question is for Arnav Vats. How can I start with IoT? Ashutosh, you are not audible.
Yeah. Now, hello,
Yeah,
hello.
now. Yeah, now we
Yeah.
can hear you.
So yeah, get some network, get some feedback, and just continue from there. And I already mentioned the sites before, right? Just refer to those to get a start. That's it.
Okay, next question is from Viplav. What languages frameworks are best suited for approaching IoT related projects? I think you already answered it.
Yes,
Okay,
yes, yes.
so our next question is from Anish. What kind of job profiles open up to me if I learn IoT and edge computing?
So basically, if you dive deeper into IoT and deeper into the hardware side of things, there's a lot of job opportunities in the embedded and low-level programmer space. There's companies like Qualcomm.
I think he got disconnected. Yeah, he is back.
Yeah, yeah, sure. So that's pretty much it. So Intel, ARM, Qualcomm, you have all of these companies that work on hardware. You have IBM that has Watson. So these jobs are typically not entry level jobs. I won't lie. Like it might not be your first job, but yeah, after you get some experience, you can get into a lot of low level developer profiles that work close to the hardware. That's where most of IoT is right now. Or you can, you can start up. That's always an option. So is there any other question?
No, that's
Yeah,
it. Okay. Thank you so
yeah,
much, Ashutosh, for joining us today
yeah,
and making it so informative. It was great to have
yeah.
you here and giving us an idea about what is IoT and edge computing in such a wonderful way. So now I would like to wrap up our event. So we also
Yeah,
have
thank
our
you.
next event at 8:30. Those who are interested, they can join with us. And to stay tuned to our new updates, do follow us on our social media platforms, Instagram and LinkedIn. To get all the updates, to visit our website. All the links are given below. Also, don't forget to subscribe to our channel and press the bell icon to get all the notifications. Thank you so much, everyone, for joining us today.
Thank you.
Okay,
Thank you.
thank
Okay.
you.